method. Should we go on with this one?
Yeah, just introduce them to it. They've got about 10 minutes. So get into it. Now, if you can follow this, our problems are gonna be cake for you. Okay, you know about cake.
We already know about cake. What about the frog cake? And it's not gonna be a cake, it's gonna be a volume, but it's gonna look like a cake. Okay. So, we'll start with our shell method now. Just so anyone who's trying to keep track, the first method we did, which was the pi r squares method, is the disk method, or the slicing method, I think it might be in the book. The second method we did, which is that outer radius minus that inner radius, that's going to be your washer method. Now this is the shell method, and the shell method is a little bit different than both of these because you have to take the idea of slicing out of your mind. Traditionally, like slicing in a line, you've got to look at more slicing in geometric shape. So,
Alright, so on their book, it's on page 402. In the calc book, it's on page 402. And then I'll make you connect next week about where it is in the IB.
okay, so we'll start with this question on the shell method, and I'll give you guys a second to write it down. Here we go. So this is going to be the shell method. At the same time, we're going to practice revolving things not around an axis. Since we've done an x-axis and a y-axis, we might as well pick an arbitrary line, rotate it around there as well. So this is asking us to find the rotation not around the axis, determining the volume of a solid bounded by y is equal to the square root of x, which we should all know now what the square root of x graph looks like, right? Everyone knows that? Okay, good. And where y is between 0 and 4 rotated around the line x is equal to 5. So once you have this problem copied, if you want to start by drawing the graph of what the bounded region looks like, you can get a bit of a head start and figure out where that is in relation to the line that we're going to rotate it around. So the first step of this, I would always recommend is to draw your functions first. So the function y is equal to radical x would be the first thing I would start with, and you would just draw that function, you know, like this. And then it starts at 0 and goes until 4, and the function y is equal to square root of x starts at 0, and you would go until 4 along the x-axis. So you get something like this. And then we're going to rotate it about a line of 5. So 5 is going to be on the outer side, and we're going to get something that looks like this. So here's our function y is equal to square root of x. It goes until 4, and then the line 5 is what we're going to rotate it around. So as you can see, we're going to end up with something that's going to look like this, which is why she's talking about cake. It kind of looks like a cake pan upside down, like one of those cakes that's hollow, like a bundt cake, yeah, a cake that's hollow in the middle. It's going to be like a little space dome, but the cylinder is going to be punched out of the middle. And this is where in the last problems, we could avoid having a complicated problem like this because we could just take it with respect to y, x didn't slice nicely, or x if y didn't slice nicely. But the problem with this one is if you slice it in the x direction, so you make slices like this all the way through, you can see like, oh, that'd be a hemisphere, we can deal with hemispheres, that one would be a hemisphere. But then as soon as you get to like this middle one, now you have like two pieces that would look kind of like this at the bottom. They're like disconnected, they're not in the middle, you don't really know where they cut off. That's where this gets complicated. And so that's why this other method exists, because slicing it in an x or y direction doesn't make sense unless you want to slice it into like 4 separate objects and then find the volume of each of them and add them. So what we're going to do instead is called the shell method.
I like your use of the word dome. You know about that? You know about that, right?
Exactly. It's going to be like a dome, but like part of it's missing.
Yeah. And they are. They're cut out, right?
They are.
And everything else I like that use. Go.
Okay, we're just, adding and logging one math. Okay. So, for each dx, what we're gonna do instead of making x a slice, dx is actually gonna be a cylinder. So, what we're gonna need to imagine is that within here, we have a cylinder that looks like this, and that we're gonna find the area of that cylinder, like this, the area of just that cylinder where the width is only as thick as dx. But then we're gonna add another cylinder around the outside of it, and we're gonna keep adding cylinders around the outside of it until we get so many infinitesimally small cylinders that they're gonna blend together into that continuous shape. Just like if we were to have a ton of little rectangles until they become a curve. And the way we do that is through integration, because this is summation, so this is like reading on sums again. So, what we need to think about is what makes up each part of these little small cylinders. What are they gonna be? Because we know that volume of a cylinder is pi r squared h. But the issue is what's, obviously pi is the same, but what's r squared and what's h gonna be? So here, the height of each of these cylinders is going to be our function y is equal to square root of x. And does everybody see why the height of this function, if you're out here on the side, is only gonna be that high? But if you're near the middle, it's gonna be like twice that high. So the height of each of those little cylinders is going to be given by the 0 along the x-axis, and it's gonna go as high as the function y is equal to square root of x. Does everyone kind of see why that's the cylinder height? And then does everyone understand why the width of the cylinder is dx, the thickness of the volume that we're going to find? Kind of. So the width of the cylinder is going to be dx because we're going to widen the cylinder. These little pieces that we're going to revolve around, think of it like taking little rectangles. We're going to take this rectangle and this rectangle, and if we revolve a rectangle around an axis, it's going to come out being a cylinder, right? And now we're revolving all these little vertical rectangles around this. We're gonna get a fuller and fuller shape where the height is gonna be given by this and the dx is gonna be the width of the cylinder. And then the radius here from the center of this object is going to be 5 minus whatever the x value is. And the reason that is because if we were to take this line that's a 4 and we revolved it around the line x is equal to 5, then the radius from there to the edge of that cylinder is just going to be 1. But if we take this point all the way at the origin and we rotate all the way around, then the radius there is going to be 4 because it's going to be the spread all the way from 5, or it's going to be 5. But if we took a point at 1, it'd be 4 because that's the spread from where that is to the center. Does that kind of make sense to people? Okay, good. So once you have that, it's pretty easy to just put into the formula because the area formula for a cylinder is 2 pi RH, which this is actually not going to be the area of the cylinder. This is going to be the surface of the cylinder. So we have 2 pi RH, which is going to be 2 pi. We're going to put on our bounds, which go from 0 to 4. We're going to take our function, which is going to be, this is here to r, and then the height is going to be radical x. So we have the 2 pi, which is going to come from the formula, and then we have r h dx. Does this make sense to everyone? For the formula 2 pi RH.
All right, now Morgan, we're gonna stop there. At this point, she's taking it far beyond. So if you were able to keep up with this, okay, really and truly, what we have to do is more along the lines of the sphere in this class. Y'all has to do something a little bit more complicated, but we have to do the sphere. So we're in very, very good shape. And you can see why I was so excited about the lecture. Because if I'm going to let somebody teach, it has to be done right. And that was done well. Very, very well. So with these last couple of minutes,